Hello guys, good evening everyone. This is week 9 and we will try to solve uh, practice problem from assignment 9 and assignment 10, and we will try to understand the shape functions, and we will also do some two-dimensional problem in linear elasticity in this week. Okay, let's solve some problem. So this is the problem from assignment 9, and in this assignment we can see that it is completely related to the nodes and shape function and etc. Okay, so let's understand and try to solve the problem. So yeah, sorry. Okay, so in this problem it is saying that we have a polygonal domain where we have meshed and we have nodes which are numbered from 1 to 6, and we have 4 elements in this domain, and there is a stiffness matrix which is indexed by I and j, and all the entries are in the ith and jth entry of the stiffness matrix. Okay, so let's see. First, we already know that what we need to do is to create a connectivity matrix. Okay, so what is the local node? First we need to write the local node. So local node, so we can see that for all elements local nodes are 1, 2 and 3. Okay, so let's see, 1, 2 and 3, and this is local node. And we need to also create a element wise global nodes, okay, which it has already given. So let's suppose for element 1 we can see that for element 1 corresponding to the local node 1, 2, 3, what are the global nodes? That is 1, 2 and 6. So we have to write 1, 2 and 6. Similarly, for element 2, what are the global nodes? That is 6, 2 and 3. So that is 6, 2 and 3. Similarly, for element 3, that is 3, 5 and 6. So we need to write 3, 5 and 6. And for element 4, So for element 4, which is 5, 3 and 4, that is 5, 3 and 4, and these are global nodes. Okay, so we can solve all these problem which is related to the indices by directly looking into this discretized domain. Like suppose we are talking about the K13. So if we talk about the K13, so we need to look into K13 nodes. So that is that one node is 1 and another node is 3, and we can see that there is no such connecting element which relate 1 and 3. So in this case we can directly mark as there is no such entry in the global stiffness matrix, so that's why we need to write 0. Okay, and we will see, like in this example K33, if I talk about the K33, then we can see that with this global node there are 4 elements which are directly connected with this node, which are 2 element number 2, element number 3 and element number 4. Okay, and the element number 4, we can see that the local node is connecting with the global node is 2, and for element 3 which is 1, and for element 2 which is 3. So which means that, yeah, from here also we can see that if I talk about K33, which means that global node 3. Okay, so here it is 3, here it is 3, and here it is 3. And since it is not on the edge, I mean there is not a sharing the edge of 2 corresponding elements, because it is directly lying on the vertices of this element. So that's why it will be the for 3, I mean for the element 2, you can see that it is directly linked with the 3 3 local stiffness matrix. Okay, and for element 3 also it is 3 3 and it is 1 1, and for element 4 it is 2 2. So for this will be, we can see that for global node 3, so we have to write for element 2 here plus for element 3 here plus for element 4 here. Okay, and for element 2, for element 2, what is the local node here? So 3 3, so we have to write 3 3. And for element 3, what is the local node? That is 1 1. And for element 4, what is that? 2 2. So it will be equal to the K13. So what is the correct answer? We can see that K233, K5. Yeah, it is not K233. It will be also, actually it should be corresponding to this. Okay, so K233, K311, K422, which means that this will be the correct answer. Now let's move to the, it is saying that what will be the entry for K55. Okay, so let's search K55, which means that the global node should be 5 and 5. So here it is 5 5, here it is 5 5. So which means that I can write it will be shared, I mean K55 will be shared by element 3 plus by element 4. Okay, now we will see where this global node is connected with the local node. So we can see that this 3 3 is connected with local node 1, so I can write 1 1. And here also 4, I mean for element 4, 3 3 is directly connected with the local node k2 2. So here in this figure also we can directly see that for 3 3, where is that node 3 3? Yeah, where is no k5 5? Here 5 5, which means that the for element 4 it will be connected with the 1 1, and for element 3 it will be connected with 2 2. Okay, so which means that what will be the answer? 3 3, yeah, k4. Okay, k4 1 1, it should be k4 1 1. k4 1 1 and k3 2 2. Okay, yeah, so it should be k4 1 1 k3 2 2. So this will be the correct answer. Now it is saying what will be the global stiffness entry for k56. So let's see for k56. So k56, where is that? So here it is 5 6. Here it is 5 6. Any other element which is shared by the local node 5 6? No. Okay, so only it is shared by element 3. And what is the local node for k56? That is 2 and 3. So that's why the answer will be k3 2 3. Okay, now it is saying what will be the global force entry F1. So let's see F1. Okay, so F1 is here, so which means that what is that element is 1, and what is that local node? That is 1. So which means that F1 1. So this is the correct answer. Now it is saying what is F2. So we need to search 2. So here it is 2, here it is 2, which means that it will be shared by element 1 plus by element 2. And for element 1, what is the local node? 2. And for element 2, what is the local node? 2. So which means that will be F12. Yeah, I think there is one more. It should be one more to yeah, no. So which means that F21 F22. So this is the correct answer. Now it is saying what will be the global force entry F3. So let's see F3. We need to search 3 here. Okay, so there are 3 3s. Okay, so here, here and here, and that will be shared by element 2, element 3 and element 4. Okay, and for element 2, what is the global node here? 3. For element 3, what is the global node? What is the local node? 1. And for element 4, what is the local node? That is 2. So what will be the answer for F3? That is F23 F31, F23 F31 and F42. So this will be the correct answer. Now similarly, what it is asking, what is F6? So let's see 6. Where is 6? So 1 6 is here, 1 6 is here. So for for the first 6 it will be shared by element 1, so element 1, and another 6 it will be shared by element 2. Okay, so for the first 6, what is the local node? 3, so it will be 3. For element 2, what is the local node? 1, so that will be F13 F21. I think there is one more C. Yeah, we need to search. I think there are 6. Yeah, there is one more, that will be for element 3 also. So for element 3, that what is the local node? 3. So 1 2 3 3 1 3, 1 2 3 3 1 3. Yeah, this will be the correct answer. Now what is the next problem? Next problem is that it is asking for the Lagrange shape function. Okay, so the first we need to write the all coordinates. Okay, so let's create for the figure 1. So here the coordinate is -1 -1, here it is 1 -1, and here it will be 0 0 and 0 -1. It will be 1 0 1 1 0 1 -1 1 -1 0. Okay, and what are the nodal position? 1 2 3 4 5 6 7 8 and 9. Okay, what is the general expression for Lagrangian shape function? So suppose I want to get the ith Lagrangian shape function, so that will be pi, and it will go from j equal to 1 to n, and it will be this minus this divided by this minus this into eta minus eta j divided by eta I minus eta j. And also here I should not be equal to j. Okay, now we will use this formula to get the Lagrangian shape function. Okay, so let's find what is n1. So where is that? Here. So what will be the? We have to multiply with all, which means that xi minus 0, xi minus 1 divided by -1 -1 minus 0 and -1 -1. Okay, and similarly eta minus 1, sorry, eta minus 0, eta minus 0 and eta minus 1 divided by divided by what will be that? That will be minus 1 minus 0 and minus 1 minus 1. So it will be xi eta minus 1, xi minus 1 eta minus 1 divided by, this will be 2 and this will be also 2, so that will be 4. So what will be the correct answer? That will be 1 by 4. This will be the correct answer. So we can directly get the shape function by using this formula. Okay, so now it is asking what is n5. Okay, similarly, I mean, we will use the same formula whatever we did for n1. Okay, so what will be the n5? That will be xi plus 1 xi minus 1 into eta minus 0 eta minus 1 divided by 1 into minus 1 divided by minus 1 minus 0 and minus 1 minus 1. So after simplification it will be eta by 2 and eta minus 1 xi minus 1 into xi plus 1. So what will be the correct answer? Correct answer will be D. And here what will be the correct answer? Correct answer was C. Okay. Now now it is asking problem number 11. This was the problem number 10. This was the problem number 9. Okay. Now it is asking problem number 11. What will be the n6? Okay. So again we will use the same thing, and when we simplify it, you will get xi minus 0 xi plus 1 divided by 1 minus 0 and 1 plus 1 into eta minus 1 eta plus 1 divided by 0 minus 1 and 0 plus 1. After simplification we will get minus 1 by 2 xi plus 1 eta minus 1 and eta plus 1. So answer will be A. Okay, now for problem number 12. So it is asking what will be the shape function for n9. So that will be xi plus 1 xi minus 1 divided by 1 into minus 1 into eta minus 1 eta plus 1 0 minus 1 and 0 plus 1. So the answer will be xi minus 1 xi plus 1 eta minus 1 and eta plus 1. So what will be the correct answer? Correct answer will be B. Now it is saying we have to use serendipity. Okay, so sir has already talked about it, and first we need to see what are the nodal coordinates. Then we will do it. So here -1, here there is a node, here there is a node, here, but there is no node here. So 1, 2, 3, 4, 5, 6, 7, 8. There are total 8 nodes only. So 0, -1, 1, -1, 1, 0, 1, 1, 0, 1, -1, 1, -1, 0. Okay. Now it is saying what is the shape function in 2. Okay. So sir has already talked about it, that we can directly use n linear shape function, that is the function of xi and eta, -1 by 2. -1 by 2. I mean, if I talk about this, okay, so we need to use linearized shape function, which is we already use for the for node 2, where this shape function will be 0 at this node and at this node, and I mean all other node except this, and minus we need to use for node 5. -1 by 2 and for node 6. Okay, so what is the linearized shape function for this 2? So that will be xi plus 1 and eta -1 divided by 1 plus 1 and -1, that will be -2. Okay, and 1 by 2, and here we have to use the shape function at node 5, where n5 will be 0 at this node, and at this node. Okay, so what will be that? That will be xi plus 1, eta -1, eta plus 1 divided by 2 times 0 minus 1 and 0 plus 1. And similarly for this part we need to use n6, where n6 will be 0 at this node and this node. So which means that what will be that? That will be xi minus 1, xi plus 1 divided by 0 minus 1, 0 plus 1, and eta minus 1 divided by minus 1 minus eta. And when you simplify it, okay, that will be zeta plus 1, eta minus 1, 4 plus 1 by 4, eta minus 1, eta plus 1, minus 1 by 4, eta minus 1, xi plus 1 and eta minus 1. And when we take a common with xi plus 1 eta minus 1, then we will get minus 1 plus eta plus 1 minus xi plus 1. So we can see that these two will be cancelled out, and if I take common of minus 1, then we will get xi minus eta minus 1. So what will be the correct answer? So N2. So N2. So here A will be the correct answer. A will be the correct answer. Okay. Similarly, if someone wants to find what is N6, for N6 it is very easy. If I talk about N6, it is very easy, N6, because we can see that N6 should be 0 at this node and this node. So we can directly write what? Xi plus 1 divided by 1 plus 1 into eta minus 1 eta plus 1 plus 1 divided by 0 minus 1 and 0 plus 1. So it will be minus 1 by 2 xi plus 1 eta minus 1 and eta plus 1. So what will be the correct answer? Correct answer will be D. Now let's move to the problem 16. It is asking to find N8, and in this case it will be eta minus 1 eta plus 1 divided by 0 minus 1 0 plus 1 xi minus 1 divided by minus 2. So that will be 1 by 2 xi minus 1 eta minus 1 and eta plus 1, and for this the answer will be A. Okay, so yeah, now let's move to the problem 16. Yeah, 16 is done. 17. So there we have to find the Jacobian. Okay, so how to find the Jacobian? First we need to get the shape function, and from the diagram this. So in this problem it is saying that we have already, where is that? Yeah, we have three shape functions n1, n2, n3, and we have to use the Gauss quadrature 0.1, 0.2 and 0.3. Okay, so first what we will do is I will import the Gauss quadrature function. Before that, like CLC clear all and sims, I will use the symbolic, so that will be xi eta. Okay, and let's import. I mean, there is no need of importing, we can directly use n1 equal to 0.25 into what is that, what is given, that is 1 minus xi 1 minus eta, that is 1 minus xi into 1 minus eta, this was n1, and what is n2? n2 0.25 into 1 plus xi 1 minus eta. So 1 plus xi into 1 minus eta. So this was this n2, and this n3, that is 0.25 into, it is 1 plus xi 1 plus eta, 1 plus xi into 1 plus eta. Okay, and let's import this Gauss quadrature 2D. So this is this function, which means that if you give the points here, it is actually a points. Based on the points, it will give the weights and xi eta. So let's do it. Let's import this Gauss quadrature point, and suppose weights 1 is for 0.1, so let's use it for 0.1, and weights 2 and xi eta 2 is for 0.2, and weights 3 xi eta 3 is for 0.3. Okay, so yeah, so that the first integral I am initializing. Integral 2 is also 0, integral 3 is also 0. Okay, and now we need to apply for loop, that is 1 to, that will be size of xi eta 1 comma 1, so which means that it will give the size, and let's take xi eta, so that will be xi k. Suppose I am taking kth element, or you can say that ith, so that will be xi eta 1, and that will be ith row and first column, so it will be xi, and similarly ith eta will be xi eta 1 and ith and second column. So these are all done, and weights, that will be weights 1, weights I will be weights 1, and here it will be ith weight, we have to take it. Okay, now integrand, what will be the integrand? Integrand will be weights I into, and here n1 we need to substitute, so subs n1 into n, what was the first, that is n3, so n1 n3, and here we need to substitute first xi as xi I. Okay, and then we need to substitute eta, so that will be eta as eta I. Okay, and then this is the integrand, and it will be stored, so that will be integral 1 will be integral 1 plus integrand. Here I will use integrand. Okay, and then it will be end. Okay, so let's check this whether it is working or not. So what, yeah, here we need to use double so that it will give in a number form. So integral 1, that is 0.1667, maybe we are, yeah, here it should be 1. Let's run this. Yeah, so it should be 0.25. Now let's go for 2 point. So here it will be 2, here it will be 2, 2, 2, and everything, I think it is correct now. It will be 2. So let's run this. 0.22. Maybe we are making some mistake here again. Okay, so wait, integrand. Yeah, here n1, yeah, okay, and we need to use n2, n3. So yeah, we are getting 0.222. Okay, now let's find third one, that is 3, 3, 3, 3 here also, and this time we have to find n1, n2. So n2, n1, nothing. Yeah, everything is fine now. Let's run this. So this time we are getting 0.222. I mean, these integrand 2 and integral 3 are approximately same. So this is all about this assignment. Now let's go to the assignment number 10. What was that? Assignment number 9, and let's go to the assignment 10. So this is the assignment. Assignment number 10. Okay. So in this assignment, it is saying that we have two-dimensional triangular domain, and there is a varying distributed load is acting on side AC, and then this is a isosceles triangle, and constitutive law is also given. Like here in this case we can see that D is E divided by 1 minus nu square and 1 nu 0 nu 1 0 0 0 1 minus nu divided by 2, and Young's modulus, it is given 100 GPa, nu equal to 1 by 3. Okay, and also there is a Neumann boundary condition which is on side AC, so which means that Ts is given, that is T naught 1 minus S divided by 2 root 2 root 2. Okay, and here there is a Dirichlet boundary condition. Okay, so we can clearly see that for each for displacement along x-axis, we can write that n1, that will be, like in this case, that will be n1, sorry, the coordinates, sorry, that will be coordinates, that will be x1 n1 plus x2 n2 plus x3 n3, and y will be y1 n1 plus y2 n2 plus y3 n3. Okay, so in this way we can write the physical domain into the master domain. Not the master domain, I mean in this case this is the same as a master domain. We can directly use, because it is the case of single element, so nothing to worry about it. We can directly use whatever we did. Okay, so now let's focus our the variational statement, and then we will try to find what we need and what we require to solve the problem. Okay, so we already saw that the shape function, I mean the variational statement, the variational statement. What is the variational statement? Variational statement is the double integral in the domain, that is or this is D, or I will use C. I mean there is nothing difference. And here it will be a traction boundary condition. Okay, so this is the variational statement. Now what we need is, we already saw that I can write x as like this, y as like this, but we already know that for the displacement along x-axis should be also a linear combination of n1, n2 and n3. So in that way, if I want to write u as u1 n1 plus u2 n2 plus u3 n3, and v I can write v1 n1 plus v2 n2 plus v3 n3, and this is the displacement along x-axis, and this is the displacement along y-axis. Okay, and if I want to write in a form of matrix, if I want to write the displacement matrix, so I can write u v as like this: n1 0, n2 0, n3 0. and similarly 0 n1, 0 n2, 0 n3, and here it will be what? u1, v1, u2, v2, and u3, v3. Okay, so this is the u and v matrix. I mean the displacement at one node, which can be written in this form. Okay, now we have to find what is the delta, I mean this delta u, that what will be the delta u. Okay, so what will be that? That will be nothing but del u by del x I cap plus del u by del y u. Okay, a j cap, that will be a j cap, which means that what we need to do, we need to find, we need to find the same thing as a partial derivative with respect to x and y. So here what we will do, we will write del y, del x, del y, del y, and it will be u and v. Okay, same thing. Now in this place, if I want to write del y, del x, del y, del y, so at the place of u and v, at the place of u and v, I can directly write in this form. Okay, so what I can write here? I want to write this. I mean, you can see that this is what? This is 2 by 1. This is 2 by 1. But what I have to write is 1 by 2. And this is what? 2 by 1. This is 2 by 6. And this is 6 by 1. Then in this case, what I have to write is, I have to write 1 by 2, which means that I have to write first 6 by 2, then 2 by, I mean in this case we need to write 6 by 2, so that will be the whole n transpose. I mean in this case that will be whole n transpose. So I can write what? So are we making any mistake here? think I did a mistake here. So it should be like this. Yeah, now it is fine. So here it should be something like this. Okay, and in this place I can directly write this thing. So that will be n, that will be n, and what will be here? Here will be u, this. Okay, so delta u will be like this. But we don't need this. What we need is, if we also if we simplify it, then it will be something, it will become something like this, that is n1 x 0, n2 x 0, n3 x 0, and here will be what? 0, n1 y, n2 y 0, n3 y, and here it will be what? Equal to, and it will be u1, u2, u3, so u1, v1, u2, v2, u3, and v3. So this is this. But what we need is, we don't need this. What we need is, we need, this is what? This is nothing but del u by del x and del v by del y. I mean, this is del u by del x and del v by del y. This is what? This is this. Okay, I mean, so this is this. But what we need, is, we need del u by del x, del v by del y, and we need del u by del y plus del v by del x. This is what we need. So in that case, what we will do is, we can write this whole thing. I mean, we already got it. So the first row, that will be n1 x 0, n2 x 0, n2 x 0, n3 x 0, 0, n1 y 0, n2 y 0, n3 y, and the last row will be what? n1 x will be n1 x, sorry, n1 y, n1 y plus n1 x, it will be n2 y, n2 x, and n3 y and n3 x, and here it will be what? u1 v1, u2, v2, u3 and v3. This is what we need. Why we need this? Because in this case, I mean the variational statement, we already saw that the variational statement here we have to use it. We have to use it because in this case we can see that this D is only 3 by 3 matrix, only 3 by 3 matrix, and we already know that the stress, the Cauchy stress will be D dot epsilon, okay, D dot epsilon. And if D is only 3 by 3 matrix, then epsilon should be 3 by 1 matrix, okay. So in that case, what is the epsilon here? Epsilon is nothing but this, okay. So that's why we need to write like this, okay. Now we can use it directly. So what will be that? That will be simply that whole integral, I mean the first part. What is the first part? The first part is the double integral del W integral D, and in this case what I can write here? I can write that suppose this is the B matrix, okay. I will assume it as a B. So I will assume it as a B matrix and U. So this is what? U. And this will be dA. Similarly, if you also write this thing as in this form only, then it will become B transpose. It will become, if I want to write this like in this form, then it will become BU, okay. And this will be DB, and DA, and it will be U. And if we use as a matrix multiplication, then I can write, and here U will not be here, okay. Let's write BU. So if we use as a matrix multiplication, then it will become U transpose, and it will be B transpose DB, and because of A, I mean the Jacobian will come into the picture, and based on that I can write dA dash, and here it will be U vector. And similarly for the traction part, what is the traction part? That is the TWDS. So that will be T dot WDS. So in that case, what we will write? That will be also U transpose and t t or we can also write like tn dot w, or yeah, t dot n, or we can also write, I mean, anyway you can write anyway, so nothing to worry about that. N transpose t, and in this case little ds will come because it will be a line integral, so it will be a ds. And what will be that? Body force. So for the body force we can write for the body force as N transpose dot bi dA. So here also N transpose dot bi, and for that J, I mean for A, the Jacobian will come and it will become dA dash. So in this way we can implement for this particular problem. So the main thing to apply for this problem is to get B matrix, then it will be solved automatically. Okay, so here also U transpose will come. Okay, so when you arrange everything, then it will be something like B transpose D B J D A dash equal to, and it will be N transpose T ds plus, and here U matrix will come. Okay, and here will be what? Double integral N transpose B I and J dA dash. So this part will be the stiffness matrix, and these two part will be the force matrix. So the main part is to get B, to get the stiffness matrix. Okay, so let's do and try to understand in the code. So this is the problem. So we can see that for the nodal coordinate for the triangular element, this is the nodal coordinate 0 0 2 0 0 2, and for the edge matrix we can see that for this edge, I mean if I assuming that this one as edge 1, this one is as edge 2, and this one as edge 3, then in the global coordinate axis we can see that this traction is actually acting in this direction. So in the local coordinate axis, I mean for this edge, there is nothing to worry about that. But if I talk about in the global coordinate, if I'm looking into in the global coordinate axis, then it will have a two component. It will have a two component like this. If suppose it is acting like this, then it will have a two component. Like if it is t, then it will be t cos theta, and it will be t sin theta. So that's why I have written 1 by square root 2 t naught this, and 1 by square root 2 t naught this. So this is the edge matrix, and suppose we are using the 0.2 Gaussian integral, and this is the local node 1 2 3, and then I have initialized k global, f global. Then first it will go to the stiffness matrix. So let's see the stiffness matrix. So I am solving this problem symbolically. So this is the nodal coordinate. I have initialized whatever the nodes. I mean there are 3 nodes, which means that we need to create 6 by 6 matrix, and the value of nu is already given 1 by 3, and E is 100. That is already given. What is that? E is 100 GPa, so that's why this is, and this is the constitutive matrix, that is 3 by 3. Now first we have to find the Jacobian. So what will be the Jacobian in this case? So let's go to the Jacobian. So Jacobian, we already saw that is nothing but the del Jacobian is what? Del x by del x. I mean del x by del zeta. But in this case, since x is zeta and y is eta, so in that case, when you partially differentiate this thing, it will become minus 0.5. I mean minus half, and this will be 0, and this will be 0, and this will be minus 0.5, 0, and 0.5, and then it will be multiplied, with nodal coordinates. Then in this way we will get the Jacobian. And the important stiffness matrix is done. Now let's move to the B matrix, which is important to calculate the stiffness matrix. So this is nothing but the Jacobian matrix, and the J is the Jacobian matrix. Then it will take the inverse, then it will take the transpose inverse, then it will find B. We can already see, we already see that this is nothing but the B. This is the B matrix, and then what will be the integrand? Integrand will be integral of determinant of G, then transpose of B, C, B, and first for the integration, the first we need to integrate with respect to x. That will go from x equal to 0 to x equal to 2 minus y. So that's why I am using here. Okay, and then y equal to 0 to y equal to 2. So in this way we will get the integrand, and it will be populated into the stiffness matrix. Now stiffness matrix is done. Let's move to the force matrix. So force matrix, we can see that this is the Neumann boundary condition, and for the N1, we already saw that to get the integral, this thing, we need to find for each edges, which means that will be 0a to n transpose TDS plus AB to n transpose DS plus BO, that is n transpose DS. So in this way, everywhere I have to first find the stiffness, we need to find the shape function. So then I will import the shape function, and we can see that for edge OA, the y will be 0. the y will be 0, then it will be integrated along x direction. Okay, and for the slant edge, we can see that on this edge y will be equal to 2 minus x. Okay, and x, for the if I want to integrate along x direction, if suppose this is s, then what will be the x coordinate? This will be s cos theta, and this will be what? 2 minus s cos theta. So that's why I have written what will be the variation of x along n2. So that will be 2 minus s cos theta. Okay, and for the left side, left edge will be x equal to 0, and it will vary from along, it will be integrated along y axis. Okay, so you can see that this will be the integration on edge 1, this is the integration on edge 2, this is the integration on edge 3, and then it will be populated. So let's run this code and we will see the result. So this is the B matrix, this is the global stiffness matrix, shape function and everything. Now let's see what are answers. First it is asking what is the shape function n1. So it's clear that we already saw that will be answer D. In this case, what will be the answer? This will be the answer. And what is the n2? n2 is x by 2, so it is clear. What is n3? n3 will be y by 2, it is also clear. Now it is saying let Bij represent the strain displacement matrix. In the lecture calculated, what will be the value of B13? So B13, so that will be a 0.5. So this will be the answer. Now it is saying 3, so this will be 3 and 3. So the answer will be 0. 26. It is asking what is B26? 2 and 6. That will be 0.5. And now it is asking which of the following represent D11. Which of the following expression represents D11? Refer the stress strain matrix for the plane stress case. So the D11, which means what it is saying? So it's not very difficult. Expression is already given. So D11, so which means that this will be E divided by 1 minus nu square. It will be E divided by 1 minus nu square. E divided by 1 minus nu square, and E divided by 1 minus 1 by 9, which means that 9E by 8. So this will be the answer. It will asking what is the D12. Again we will use whatever it is given. What is that? E12 means nu E divided by 1 minus nu square. Nu E divided by 1 minus nu square. Nu E divided by 1 minus nu square, which means that what was that? E divided by 1 minus nu square, 9E by 8. So multiply with nu, that will be 1 by 3. So it will be 3e by 8. So 3e by 8 will be the answer. What will be the d22? So d22, again the same answer will come, that is the e divided by 1 minus nu square, 9 e divided by 8, same answer will come. Now it is saying which one of the following is the Dirichlet boundary condition for this problem. So if I talk about, this was the condition. This is the node 1, 2 and 3. So we can see that this node is not able to move along this direction and this direction, which means that alpha 1 equal to 0, alpha 2 is also equal to 0. But for this node, and what is that? That will be alpha 3 and alpha 4, and here it is what? Alpha 5 and alpha 6. So in this case you can see that it is able to move along 3 direction, but it is not able to move along y direction. So that's why alpha 4 equal to 0. And in this case